All right, let me show you a quick example of how some of these summation formulas that you saw in the previous video apply to what we were looking at in the previous section for finding area under curves. It turns out that those formulas will allow us to find the exact area under some curves. So here in this example, we're going to find not an estimate to the area under the graph of x squared from 0 to 1, but the exact area under this graph. All right, so this function y equals x squared, we know, of course, what that looks like. We're not worried about the whole function, we're just worried about this function between 0 and 1. And so that's what we're looking at over here. I zoomed in on just this piece of the graph, and our goal is to find out what the area of this shaded region is. All right, so we know how to do this. Let's do, well, we know how to do an estimate. Let's do an upper sum. All right, so an upper sum, let's do with two rectangles. If I'm using an upper sum with two rectangles, I need two subintervals here, from 0 to 1/2, and then 1/2 to 1. If I'm doing the upper sum, then over each interval, I'm going to pick the high point on that interval. So I'd come here, and there's my first rectangle, and then come here, there's my second rectangle. All right, so our upper sum with two rectangles would be, well, what's the base of these? The base of each rectangle is 1/2. What's the height? Well, the height comes from plugging these x values into my function. So this y value here is 1/2 squared, so that would be 1/4. This x value here would be 1 squared, which is 1. Right, because we just square our x values, we're doing the function x squared. All right, so I would have 1/2 times 1/4, that's base times height for my first rectangle, plus 1/2 times 1, that's base times height for my second rectangle, and that gives me my upper sum for two rectangles. All right, and we could go ahead and figure out what this comes out to. I'm not too concerned about the final answer here. I'm just using this to illustrate the general concept that we'll be using to figure out the exact area. Let's see, so let's go ahead and get this in for this particular case. That's 1/8 plus 1/2. Let's see, that's 1/8 plus 4/8, so that's 5/8. All right, so that's an overestimate to the total area under the curve because we have all this extra stuff going on that's not actually under the graph. Now, let's bump this up. We talked about in the previous, or one of our previous lessons, that we can make this better if we do more rectangles. So what does all of this look like if we do 3 rectangles? And then after we do 2 rectangles and then 3 rectangles, let's see if we can generalize this to just any number of rectangles so that we can get a better idea of what's going on. All right, so let's do this again with 3 rectangles. So in this case, I need to break this up into thirds. So I've got 1/3, 2/3, and then 3/3 is 1. Same thing, we're doing an upper sum, so I need the right endpoint is going to give me the high point of each interval. So that'll give me the height of my rectangles. So now, what's the base for each of these rectangles? Each of them has a base 1/3. And now I'm just gonna, since we use that 1/3 over and over again, I'm just gonna factor that 1/3 out. And and then I need to add up the heights of the rectangles. This is 1/3 squared, which is 1/9. This one would be 2/3 squared. And then this last one, the height of that third rectangle would be 1 squared, which is 1. And actually, to help us see where our general formula is going to come from, I've got 1/3 squared, 2/3 squared. I'm going to write this as 3/3, which is the same thing as a 1. 3/3 squared. All right, so 1/3 squared, 2/3 squared, 3/3 squared. Now, let's see if we can do an upper sum for n rectangles. Let's generalize this. See if we can pick up on the pattern here. Upper sum for n rectangles. So if we have n rectangles, what's the base of each rectangle going to be? Let me draw our picture real quick. So if we're doing n rectangles, then we're splitting this interval between 0 and 1 into n pieces. So I'd have 1/n, 1/n, 2/n, and then however many, whatever n is, out to finally at 1, this would be n/n. All right, and then again, if we use the right endpoint to get the height of each interval to give us this upper sum, then eventually we get n rectangles. And then we add up the area of each rectangle. Well, what is the base for each of these rectangles? The base for each rectangle is 1/n. What's the height of each rectangle? Well, we take the x value and square it because we're doing f of x equals x squared. All right, so we've got 1/n squared plus 2/n squared plus 3/n squared all the way out to plus n/n squared. So I've got my base for each rectangle, and then the height of each rectangle added up here. I've got the sum of the heights of the rectangles. Now let's connect this to our sigma notation. Now, before I write down the sigma notation, remember the whole idea is if I can do more and more rectangles, like we've seen before, the more rectangles I do, the closer I am to the exact answer. All right, so where we're headed with this is if I can write down this expression for the sum of n rectangles, I can let n get really big using what we know about limits. All right, so we're going to take this and we're going to do the limit as n goes to infinity. That will give us our exact answer. All right, but before we do any limits, let's just see if we can rewrite this using sigma notation. All right, so let's come up here, and how can I write this using sigma notation? Well, this 1/n is not part of my sum. I can write that out outside of the sigma notation. 1/n, and then what am I adding up? I'm adding up 1/n squared, 2/n squared, 3/n squared, and so on, all the way to n/n squared. So the way I can write that is I can go from I equals 1 to n of I/n squared. Right? You can double check that. this is exactly what we have inside the parentheses for the sum of our heights down below. 1 over n squared plus 2 over n squared, and so on. And we stop when we get to n over n squared. All right, now let's connect this to the summation formula that you saw in the previous video. So first of all, this is 1 over n times the sum I equals 1 to n of, I'm going to split this up into two pieces. This is 1 over n squared times I squared. Okay, now something you need to understand here is n is a constant as far as the sum is concerned. The sum is adding up over the index I, and so this 1 over n is just the number of rectangles that we're using. All right, so as far as this sum is concerned, 1 over n squared is a constant, so constants can come outside of sums. So this is 1 over n times 1 over n squared, and then we've got our sum from I equals 1 to n of I squared. Now obviously 1 over n times 1 over n squared simplifies to 1 over n cubed. And we have a nice formula for the sum of I squared for I going from 1 to n. Okay, so the formula that we got from that previous video, this was n times n plus 1 times 2n plus 1, all divided by 6. And now I can simplify this a little bit further. I have an n on top, an n cubed on bottom. I can reduce this down to n squared. So I have n plus 1 over 2n plus 1, or times 2n plus 1 over 6n squared. So now this expression gives me the area, or the upper sum, for this graph for n rectangles. Okay, so what we've just written down here, no matter what n is, if I want the upper sum for n rectangles, this right here gives me that upper sum, n plus 1 times 2n plus 1 over 6n squared. So if I wanted to do the upper sum for 10 rectangles, I don't need to do it manually. I can just go straight to this formula, plug in 10 for n, and get my answer. If I wanted to do my upper sum for 100 rectangles, I don't need to do that by hand. I go straight to this shortcut formula and plug in 100 for n and get my answer. All right, so this is a great shortcut we can use to find the upper sum, in this case for x squared, from 0 to 1 with n rectangles, where n can be any number we want. All right, so now let's come back to our original question. We want the exact area. The exact area isn't what we have down here. This is still just an upper sum. This upper sum is not the exact area. This is just an estimate to the area. But again, like we've said, the exact area will be what happens as n goes to infinity. So for my exact area, if I do the limit as n goes to infinity of my upper sum for n rectangles, I'm going to get my exact area. This is a limit we know how to do. It may help if we multiply out that numerator. If I multiply out the numerator, that would be 2n squared plus 3n plus 1, all divided by 6n squared. Now as n goes to infinity, the top is going to infinity, the bottom is going to infinity. This is an indeterminate form. You can do this limit using L'Hopital's rule, or you can use our trick from the beginning of the semester and divide out that n squared from everything. Or you could also think of it as just breaking this fraction up into 3 pieces. This is the same thing without even needing L'Hopital's rule in this case. Using our easier trick from earlier in the semester, this is the same thing as 2n squared over 6n squared. That would be 2 over 6 plus 3n over 6n squared. That would be 3 over 6n. Because here when I'm looking at 3n over 6n squared, the n's cancel and leave you with just n to the first power on bottom. Okay, and then when I look at my last piece, I'm doing 1 over 6n squared, so plus 1 over 6n squared. Now what happens as n goes to infinity? This term goes to 0, this term goes to 0, and we're left with just 2/6. So as n goes to infinity, I'm left with 2/6, which is the same thing as 1/3. So this number I just got here, this 1/3, let me make sure you understand what that number represents. That number is the exact area under my graph. Let me come back over here to this graph that we were looking at. If I look at this graph, and I'm doing the exact area under this thing, not just an estimate, but the exact area of this entire region under this graph, I can get that by doing an upper sum with n rectangles, like we did here, and then see what happens as n goes to infinity. As the number of rectangles increases, I get closer and closer to the exact area. And finally, when we compute this limit, the limit as n goes to infinity for this upper sum is the exact area. So the exact area under the graph of x squared between 0 and 1 is 1/3. Whatever our units are, 1/3 meters squared, 1/3 feet squared, 1/3 inches squared, it doesn't matter here. The area under the curve is 1/3 units squared. So let me show you where we're headed with all this in the next lessons. All right. Suppose that we want to find, again, not an estimate, but the exact area under the graph of some function over this interval from a to b. Now, on the previous slide, we did this specifically for x squared, and the interval that we looked at was 0 to 1. All right, but I want to just generalize this further. What's the general idea for finding the exact area under some arbitrary function? I'm not going to tell you what the function is here. Find the area under some function over some interval a to b. All right, so we know how to get an estimate, right? We can do these upper sums or lower sums or midpoints or all kinds of things, but it all just boils down to, if I want to estimate the area under this graph from a to b, this region here, if I want to estimate that area, then I just add up the area of n rectangles, right? And what this looks like is the area of a rectangle is base times height. All right, so if I'm doing n rectangles, then we need to know, how wide is each rectangle. That's one of the elements that we need. All right, and I'm going to use a symbol here to represent the width of each of these rectangles. I'm going to call this delta x, which means how much my x values are changing. All right, so the width or the base of my rectangle, I'm just going to call this delta x, or change in x values. So that's my base for my rectangles. And now my height, you're picking some x value in here and using that to define the height of the rectangle. So basically it just boils down to, you've got some x value and you use that to pick out the height of that rectangle by plugging that x value into the function. So you've got x1, you can plug that into the function. You can take x2, wherever that is, plug that into the function, get your second rectangle's height, and continue on. x3, x4, you're just taking these x values and plugging them into your function. So the height of each rectangle would be whatever you get when you plug these x values into your function, f of x sub I. F of x1, f of x2, f of x3 gives you the height of the first rectangle, the second rectangle. All right, so we've got the height of each rectangle. We've got the base for each rectangle, and then we're adding up the areas of those rectangles, base times height. That gives me an estimate to the area. Now, what we saw on the previous slide, the base was 1 over n, and the height was our x value squared. But that's not always going to be the case, right? That was a special example where f of x was x squared and our interval was 0 to 1. If our interval is from a to b, then we have to calculate, okay, what would be the base in that case, and then figure out the height. The height depends on the function. Last time we were doing x squared, but this could be whatever other function. So this is what we were doing last time on the previous slide, but now I'm just kind of generalizing the idea. So this gives me an estimate to the area. How do I get the exact area? And again, we've already talked about this. If I want a better estimate, what do? I do more rectangles. So my exact area is going to equal the limit as n goes to infinity of this sum that we have written down here below. The sum of the height of each rectangle, f of x sub I, times whatever our width of the rectangle is, whatever the base of the rectangle is. And we're going from I equals 1 to n, where n represents the number of rectangles, but then we're taking the limit as the number of rectangles goes to infinity. That gives me the exact area under any function from a to b, assuming there may be some requirements on that function, but assuming that this area is defined, this will give me the exact area under that function between a and b. Now, on the previous slide, this all worked out nicely because I was able to use one of our nice sum formulas to simplify the I over n squared is what we were doing on the previous slide for this f of x sub I, and that delta x was 1 over n. I was able to use summation formulas to get a nice answer there, but what if this is some other formula where we don't have a nice little shortcut to use? Then what do? What if this is an uglier function, like maybe a trig function or an exponential function or a logarithmic function? I can handle something, maybe like x squared or x cubed, because we have nice formulas for handling those. But what do we do with uglier functions? Well, where we're headed next is what we call the fundamental theorem of calculus. And it's crazy that at the end of a calculus semester, we finally learn what's called the fundamental theorem of calculus. But the fundamental theorem of calculus will tell us exactly how to get this area. All right, so this is kind of the concept, this limit as n goes to infinity, but how do we actually calculate this in practice? We need a theorem for that, and the theorem is called the fundamental theorem of calculus. And that's where we're headed next. You're not going to see it in this lesson, but this is what's coming up next week. All right, so that's something you have to look forward to in our next few lessons. We'll learn what this theorem is all about.